Alright team, so we're going over exponential and logarithmic functions. Here are our basic concepts. And so we have two formulas going on, a general and a continuous, and one we already did an example with, retirement system in the 401ks, and the mutual funds involving the general formula for exponential growth, and a little later we'll get into the continuous one. So let's bring it back down into a more simpler example. Let's say we had population of 752,000, and it increases at 1.4% for 18 years. Okay, and so what will the population be at that time? That's the idea, that's our question. Let's figure it out. And so we have to use our general formula here. We have 752,000 as our principal, and our rate of increases, so it's going up, that means it's growth, and they're doing this per year, so one time per year is our compound, and 18 years for the total time. So our area, or sorry, not area, amount, will equal the principal of 752,000, and then multiply that by 1 plus the rate of 0.014, because that's what it would be, 1.4% would be in decimal form, and our compound, number of times compounded, will be 1, and then to the 1 times 18, well, that's 18, okay. So this would just be 0.014 divided by 1 is the same number, so it'd just be 1 plus that, so 1.014 to the 18th power times 752,000. Okay, let's go ahead and see what we get here. And so if we type that in, we'd have 1.014 to the 18th power. And so take that number, multiply it by your principal of 752,000, and your population after all that time will be about 965,830.75. Well, you can't really have 0.75 of a person, you can't have 3/4 of a person, so let's go ahead and round this to a full number. And so our amount, our population will end up being 965,831. We'll round up. Okay, let's take a look at a different example. What if we have a car that was to depreciate in value after you purchase it? So here we have a new car. It sells for $18,000, and it depreciates 25% each year for 4 years. So what's that one gonna look like? Well, let's figure it out. Okay, so we have our amount will equal the principal of 18,000. And then depreciate means this is going down in value, so we'll have 1 minus our 0.25 for 25%. Each year means once a year for 4 years, so 1 times our 4 years is 4. Okay, let's go ahead and type this in, see what we have here. So here's our calculator, let's clear the old problem. So 0.25 divided by 1 is 0.25, so 1 minus our 0.25, we're at 3/4 or 0.75. Take that to the 4th power. So we have this number, multiply that by our principal, and looks like our car after 4 years is going to be a little over $5,000. That is a huge drop. Okay, so $5,695. Oh, and 31 cents. Don't forget about the 31 cents. Okay, let's look at one more example. And this time I'll do a part A and a part B. So let's say we had, that we deposit $3,000 in a bank account. This bank account that pays yearly interest rate of 3%. How much money will be in the account after 5 years? If the interest is compounded quarterly, or B, the interest is compounded continuously. Okay, let's go ahead and see what we have here. So part A, we know what to do. It's what we did previously. Let's go ahead and figure that out. So part A over here, we can do this one right now. Because we know the principal is 3,000. And let's see, so interest rate, it's not a negative interest rate, so we are adding our 3%. Divided by, let's see, compounded quarterly. Well, quarterly would be 4 quarters in a year, $1, anything like that. And then this exponent changes, it's not just 5, it's going to be our compound number times our time, multiplied by our time. So that would be 4 times 5 in our power right here for our exponent. And yes, you could write 20 right away if you want to. Let's go ahead and calculate this. So we have, well, let's take care of our parentheses first. So 0.03 divided by 4 would be 0.0075. Okay. 1 plus that number will give you 1.0075. Take that to the power of 4 times 5. So take this number to the power of 20. and then we multiply that by our principal of 3,000. So it looks like our answer will be $3,483.55 after 5 years. Okay. So $3,483.55. Not bad for having the money just sit in the bank. Okay. Well, part B, let's see if what this would return if it was compounded continuously. And so above we had the formula, the amount would equal our principal times e to the r times t. Okay, well, e is just a number. It's a constant number, kind of like pi. And so e, we refer to that as Euler's number. And Euler was a Swiss mathematician. And here is basically, if I could confuse you for a little bit, this number, letter e, is derived from this. It's 1 plus 1 over n to the n. So very similar to what we had going on right here. The only difference is, what if we took letter n to infinity? What if that was a very large number? In fact, so large, we'd call it infinity. What would that look like? Well, you could take this and make it a binomial distribution and have that number equal 1 plus 1 divided by 1 factorial plus 1 divided by 2 factorial plus 1 divided by 3 factorial, and so on and so forth. Okay, that doesn't really help us out, so if you take this chart, this one might help you out. If you take this chart right here, let's say you had this function. Here, let's make that a little bigger. If you had this function, well, yearly, you'd have 1 over 1 to the first power. Well, that equals a 2. Well, semi-annually, okay, so we have a 2 up in the power, we have a 2 up here underneath in our denominator, that equals 2.25. Okay, quarterly, that means we have 4 there and 4 there, 2.44. So let's go all the way down to every second. So every second, well, this is how many seconds in a year, and you can see the number gets right around here, 2.718, and so on and so forth. And that is what the number would be, and so you could keep getting this number to be larger and larger, hence infinity, and it becomes a constant, kind of like pi. So these numbers, the decimals, would keep on going forever and ever, and getting you about 2.718 and a bunch of more digits as your constant for Euler's number. Okay, so that's a very rough explanation of where that number is derived from. However, we can just use it because our amount here, for having it something compounded continuously, we'd have our initial principal of 3,000, and then multiply that by e to the rate, which is 3%, multiplied by our time of 5 years. And so, let's calculate that. And so, here is our function e, hey, there's our number we just had, to the power of 0.03 times 5. And I didn't add parentheses, so let me redo this. So we have e, very important to have parentheses, to the power of 0.03 times 5. Close our parentheses, much better, and then hit enter. So it looks like we almost have the same number as before in part A. Multiply that by our principal of 3,000. And hey, looks like we made a little more money if something were to be compounded continuously. $3,485 and 50 cents. Alright, so there you have it. And this would be the general pattern if you have all the same parameters, and the only difference is the compound. Well, you obviously want things to be compounded more often. That's in your interest because it makes you a little more money. If you're the bank, you would want to not compound things continuously. You would compound them as few times as possible to store people's money, saving you a little bit in time. Alright, there you have it. Here are exponential and logarithmic functions. Good luck in your practice.